Follow a single particle of sunlight outward. 8 minutes, and it crosses the Earth. 4.5 hours, and it passes Neptune. 17 hours, still inside the same day it left, and it is beyond the heliopause, past every object human beings have ever built, landed on, or photographed. Everything our species has ever reached fits inside 17 hours of light. Now keep watching, because that same particle travels another 28 days before it reaches the near edge of the outermost region of the solar system, and something like a year and a half before it is past the far side. Light takes 18 months to leave the solar system, and the place it takes that long to cross has never been seen. Not one object in it, not once, by anyone. By the end of tonight you will know exactly how far away the Oort Cloud is, and why that answer melts on contact. Get cozy. If you're the kind of person who enjoys having a familiar sense of scale quietly dismantled, hitting like and subscribe genuinely helps this channel reach more curious minds like you. Because by the end of this, the phrase leaving the solar system will have stopped meaning anything at all. Now let's ease down into this slowly. There is a picture of the solar system in your head, and it is wrong in a very specific way. You know the picture. The sun sits on one side, usually too large, usually too yellow. The planets run out from it in a neat line, sometimes a neat curve, and the whole thing fits comfortably on a single page. Mercury, Venus, Earth, Mars. A gap. Jupiter, Saturn, Uranus, Neptune. Perhaps a small grey dot labelled Pluto, added or removed depending on when you were at school and how strongly your teacher felt about the subject. And then the page ends. The border of the diagram arrives, and the solar system stops, because the paper stops. That picture is not a simplification. A simplification would be a version of the truth with some details left out. This is something else. If you drew the solar system to scale on that page, and you put Neptune at the outer edge of the paper, where the diagram normally ends, then the actual outer boundary of the solar system would not be on the page. It would not be in the book. It would not be in the room you're sitting in. To keep the same scale, you would need to walk out of the building, out past the end of your street, and keep walking for the better part of an hour before you reach the place where the sun finally lets go. Everything in that familiar diagram, every world, every moon, every ring, every mission any human being has ever flown, every photograph ever returned from another planet, occupies the innermost sliver of a structure so much larger than itself that we do not really have a word for the relationship. Not the inner half, not the inner tenth, something closer to the innermost 3/10,000ths. The rest of it is a place called the Oort Cloud, and nobody has ever seen it. I want you to hold on to that sentence tonight, because it is going to come back several times before we are finished, and each time it comes back it will mean something slightly different. Nobody has ever seen it. Not through a telescope on a mountaintop, not through a telescope in orbit, not with infrared, not with radio, not with the largest arrays we have ever built or the longest exposures we have ever taken. There is no photograph of the Oort Cloud, because there has never been anything to photograph. Not one single object has ever been observed sitting where it lives, and yet it is, by an enormous margin, the largest thing the sun holds on to, and it may contain more individual worlds than every other part of the solar system combined. Let me tell you what we think is out there, and then let me tell you how strange it is that we think it. We think that at some distance beyond everything familiar, the sun is surrounded by a shell of icy bodies. Not a ring, not a belt, not a disk lying flat in the plane of the planets. A shell, wrapping the entire solar system in every direction, above and below and around, the way the skin of a balloon wraps the air inside it. We think it contains hundreds of billions of objects at minimum, and quite possibly several trillion. We think each one is a mountain of frozen material a few kilometers across, dark as fresh asphalt, sitting at a temperature only a few degrees above absolute zero, drifting so slowly along its orbit that a commercial airliner could outrun it. It is worth separating this from something you may already have heard of, because the two get confused constantly, and the difference turns out to matter enormously. The Kuiper Belt is real, it is well studied, and we have flown a spacecraft through it. It is a flattened disk of icy bodies, lying roughly in the same plane as the planets, running from about 30 times the Earth's distance from the Sun out to about 50. Pluto lives there. It is the source of most of the comets that come back on human timescales, and it is not what we are talking about tonight. The Kuiper belt is a ring on a table. The Oort Cloud is a room the table is standing in, and the room is so large that we have never found a wall. NASA has a description of these objects on its own public fact page that I have never been able to improve on, and I am not going to try. They say that in the silence and the darkness between the stars, where our sun appears as just a particularly bright star, these icy objects coast along their orbits like lazy moths around a porch light. That is a warm image. It is a domestic image. Moths around a porch light is a summer evening, a back door left open, something you have actually stood underneath. Keep it. We are going to come back to the porch light at the very end of tonight, and when we do, it will have changed into something else entirely. So how far away is it? That is the question, and I am going to be honest with you about the shape of tonight before we go any further. I am not going to answer that question yet, not because I am withholding a number for effect, but because the number is not the answer, and if I gave it to you now, you would nod, and you would file it away somewhere next to all the other large numbers you have been handed over the years, and nothing would happen to you at all. Here is what I mean. I could tell you a distance in miles right now. I could give you a figure with 13 digits in it, and you would hear it as a sound rather than a quantity. Large numbers stop being numbers somewhere around the point where you can no longer count to them, and beyond that they all feel roughly the same. A trillion feels like a billion feels like a quadrillion. Your intuition simply flattens out and refuses to distinguish between them. So instead of giving you the number, I am going to do something slower and, I think, considerably worse for your peace of mind. I am going to take you out there using every measuring tool we have, every ruler, miles first, then the astronomical unit, then the speed of light, then the fastest spacecraft we have ever built, then the orbital periods of the objects themselves, and finally the entire span of human history as a unit of measurement. And what I want you to notice as we go is that each one of them breaks, not gradually. Each ruler works beautifully for a while, and then fails, suddenly and completely, at a different point along the journey and for a different reason. Miles fail first. The astronomical unit lasts a little longer. The speed of light, the tool we normally reach for precisely because it makes cosmic distances feel manageable and friendly, turns around at a certain point and starts making things worse. Spacecraft fail after that, and human history fails last and hardest. By the time we get to the end, you will have the number. I promise you the number. But you will also, I hope, understand why the number is not the interesting part, and why the true answer to the question is stranger than any figure I could read out to you. For now, let us start at the last place you have a solid mental footing. Voyager 1 left the solar system. You have heard that sentence. It was in the news in 2012. It has been in the news several times since, and it is one of those facts that has settled comfortably into general knowledge. The little spacecraft from the 1970s still transmitting, finally crossing over into interstellar space. That sentence is true in one specific technical sense, and badly misleading in every other sense. What Voyager 1 crossed in 2012 was the heliopause, the surface where the wind of particles streaming out from the sun finally runs out of push and gives way to the thin gas between the stars. It is a real boundary. It is a genuinely enormous achievement to have reached it, and it sits at roughly 120 times the distance from the Earth to the Sun. The Oort Cloud does not begin at 120. Its inner edge is thought to lie somewhere between 2,000 and 5,000 times the Earth's distance from the Sun, and its outer edge is somewhere between 10,000 and 100,000. So Voyager 1, which left the solar system, is not a 50th of the way to the near edge of the outermost region of the solar system. It is not a 100th. Depending on which end of that range you take, it is somewhere between 1,000th and 1,500th of the way to the far edge. Which means there is a version of this story where the spacecraft that left the solar system has, in almost half a century of continuous travel, covered about 1/10% of the distance to the place where the solar system actually ends. And I have not even told you yet what that place is made of, or how we know it is there, or what happened 70,000 years ago when something came through it while human beings were already alive and watching the sky. Let us throw away miles, because miles were never going to survive this. The problem with miles is not that they are too small, it is that they are the wrong kind of unit for the job. Miles are a walking unit. They come from a human body moving across ground, and they carry all of that with them. The sense of an afternoon, of a distance you could cover if you were determined, When you stretch a unit like that across the solar system, it does not scale up. It just produces strings of digits that your mind processes as noise. So astronomers replaced it with something honest. The astronomical unit is simply the distance from the Earth to the Sun, roughly 93 million miles, or 150 million kilometers. It is a lovely unit because it is anchored to something you have actually experienced. You have stood in sunlight. That sunlight crossed one astronomical unit to reach you. The unit is not abstract at all. It is the length of the thing that warms your face in the morning, and for most of the solar system it works. Mars is 1.5, Jupiter is 5, Saturn is 9.5, Neptune is 30. Those numbers sit comfortably in your head. You can arrange them, compare them, feel the gaps between them. 30 is a number you can count to. Then you try to use the same unit for tonight's subject, and it dies immediately. The inner edge of the Oort Cloud is somewhere around 2,000 to 5,000. The outer edge is somewhere between 10,000 and 100,000. And the moment you say 100,000 astronomical units, the unit has stopped doing its job because you cannot feel 100,000 of anything. You have never counted to 100,000 in your life. Nobody has. The unit that was supposed to make the solar system comprehensible has been asked to do something it simply cannot do. So we reach for the tool we always reach for when distance gets difficult. We reach for light. Light is the great comforter of astronomy. It is the unit we use when we want to make something enormous feel intimate. The moon is 1.25 seconds away. That is nothing. That is a pause in a sentence. The sun is 8 minutes away, which is about how long it takes to make a cup of tea. Mars at its closest is 3 minutes away. When you convert distance into time, the solar system suddenly stops being a horrifying set of numbers and becomes a set of errands. Light time is friendly. Light time is the unit that makes space feel like a neighborhood. Now watch what it does here. I want you to travel with a single particle of light. It leaves the surface of the sun, and it does what light always does, which is to move at exactly one speed, forever, without accelerating, without tiring, without any sense at all of how long it has been going. There is a small piece of context worth adding before it starts, because it changes the texture of the journey. That particle did not begin its life at the surface. It was created far down in the core of the sun, and before it could leave, it had to fight its way out through the star itself, absorbed and re-emitted, over and over, scattered in random directions, drifting outward at a crawl through material so dense that light behaves less like a beam and more like a rumour. Estimates for how long that takes vary enormously depending on the model, but the common figures run to tens of thousands of years. The particle we are about to follow has already spent longer inside the sun than our species has spent farming. Its trip across the entire solar system will be the easy part. 8 minutes in, it crosses the Earth. Behind it, the sun is already an 8-minute memory. Ahead, there is nothing but dark. 4.5 hours in, it crosses the orbit of Neptune. That is a full working day's afternoon, and it has already passed the last planet. In another 3 hours, it is beyond the outer edge of the Kuiper Belt, past Pluto's neighbourhood entirely, past the last population of objects that anyone has ever visited or photographed at close range. 7.5 hours out, 12 hours after that, 17 hours total still inside the same day it left. It passes the heliopause. This is the boundary Voyager crossed. This is where the solar wind gives out and the interstellar medium begins. Our particle of light has now travelled farther from the sun than any object human beings have ever built, and it has done it in less than 1 day. 17 hours. Hold that number. That is the entire reach of the human species, converted into light time. Everything we have flown, everything we have landed on, everything we have imaged, everything we have touched, all of it fits inside 17 hours of light. And here is where the friendly unit turns on you. That same particle of light continues. It does not slow down. It has no reason to. And it travels for another 10 days at minimum, and possibly as long as 28 days, before it reaches the inner edge of the Oort Cloud. Not the middle, the near edge, the very first place where you might reasonably expect to find one of these icy objects. 28 days, nearly a month of continuous travel at the speed of light, after having crossed everything humanity has ever reached in 17 hours, and then it keeps going. And to pass beyond the outer edge, to finally be clear of the whole structure, to be genuinely outside the region the sun claims, that particle of light travels for something like a 1.5 years. If that ratio is still too abstract, try compressing it. Imagine the whole 17-hour crossing of everything humanity has ever reached squeezed down to a single second. 1 second. On that same scale, the crossing of the full Oort Cloud would take about 13 minutes. You could say the sentence, "We have left the solar system," and then sit in silence for a quarter of an hour before the claim became true, and there is no clever way around it. This is one of the details about the Oort Cloud that people miss on the first pass, and it removes the last available comfort. Because the structure is a shell rather than a disk, because it wraps the sun in every direction rather than lying flat in the plane of the planets, there is no thin edge to aim for. You cannot go up and over. You cannot dive below and come out the bottom. There is no orientation you can choose, no angle of departure, no clever trajectory that shortens the crossing. Straight up out of the plane of the planets is exactly as far as straight out along it. The distance is the same in every direction you could possibly point, which is a very unusual property for a journey to have, and a thoroughly unhelpful one. I want to be very precise about what has just happened, because it is easy to let it slide past. Light is not slow. Light is the maximum. It is not merely the fastest thing we know of, it is the fastest thing that can exist. There is no faster, and the tool we invented specifically to make cosmic distance feel small has just told us that the solar system takes 18 months to cross. 18 months is roughly 13,000 hours. 17 hours is 17 hours. Divide one into the other, and you get about 770. Everything the human species has ever done in space is 1/770th of the way out, measured in the only currency the universe actually respects. There is a detail buried in that journey that I find harder to shake than the numbers themselves, and it is this. Along the entire route, absolutely nothing happens. There is no marker at the heliopause. There is no line, no wall, no flash, no change of colour. Voyager did not fly through a membrane. It measured a shift in the density and the direction of the particles around it, and scientists on Earth spent months arguing about the data before agreeing that it had crossed. The greatest boundary in our solar system announced itself as a change in a graph, and the Oort Cloud will be worse. There is no inner edge in the sense of a surface. There is a region where, statistically, you would begin to encounter these objects, if you could see them, which you cannot, and if you were anywhere near one, which you almost certainly would not be. A spacecraft crossing into the Oort Cloud would register precisely nothing. The instruments would report the same emptiness on both sides, so the first ruler has broken. Miles gave out immediately, the astronomical unit gave out at about 1,000, and light time, the unit we trusted most, has done something worse than break. It has held perfectly, remained completely accurate, and delivered an answer that makes the problem larger rather than smaller. Which leaves the obvious question standing there, unanswered and getting heavier. If nobody has ever seen this place, and no instrument would notice crossing into it, and light itself takes a year and a half to get past it, how do we know it is there at all? That question has a name attached to it, and a year and a single sheet of numbers. In 1950, in the Netherlands, an astronomer named Jan Hendrik Oort published a paper with a title that gives away nothing at all. It is called The Structure of the Cloud of Comets Surrounding the Solar System and a Hypothesis Concerning Its Origin. It ran in the Bulletin of the Astronomical Institutes of the Netherlands, Volume 11, pages 91 to 110. There are no photographs in it. There are no images of anything. There is no observation of a new object, no discovery of a moving point of light on a plate, nothing that would look like discovery to anyone who has ever watched a film about astronomy. The entire evidentiary foundation of the largest structure in the solar system is a table of numbers, 19 numbers to be precise, 19 comets. Oort was not, at that point, an obscure figure looking for a subject. He was one of the most consequential astronomers alive. 2 decades earlier, he had helped establish that our galaxy rotates, and rotates differentially, with the inner parts going round faster than the outer parts, and he had produced an estimate of how far the sun sits from the centre of the Milky Way. He had spent his career working out the shape of things he could not step outside of and look at. He was, in other words, extremely good at the specific mental move that this problem required. Here is the problem he was working on. Comets had been a nuisance to theory for centuries. Some of them come back on schedule. Halley's Comet returns every 76 years, which is short enough that a person can, if they are lucky with their birthday, see it twice. Those are tidy. They orbit in more or less the same plane as the planets, they go around in the same direction, and they behave like members of the family. But there is another kind. These are the long-period comets, and everything about them is wrong. They arrive on orbits so stretched out that they barely count as orbits at all. They come in at every conceivable angle, from above the plane of the planets, from below it, from the side, tilted, sideways, backwards. They do not respect the direction the planets go round, and most of them are seen exactly once in recorded history and then never again, because whatever schedule they are on is longer than civilization. If comets came from a disk of leftover material near the planets, this would be impossible. A disk produces comets in the plane of the disk. That is what disks do. But these arrive from every direction on the sky with no preference at all, which means the reservoir they come from cannot be a disk. It has to wrap around us. That was the first half of the argument, and it had been noticed before. What Oort did was the second half, and the second half is arithmetic. Every orbit has a size described by a quantity called the semi-major axis, essentially the average distance from the Sun over the whole orbit. For a comet on an enormously stretched path, that number is enormous, and the more nearly it approaches an open, unbound trajectory, the larger the number gets. So astronomers usually work with its reciprocal instead, 1 divided by the semi-major axis. That flips the scale around. A very tightly bound comet has a large value. A comet on an orbit so enormous it is barely holding on has a value very close to 0. And an object that is not bound to the Sun at all, a genuine visitor from outside, comes out on the negative side. Oort took 19 long-period comets whose orbits were known well enough to trust. He did something careful and slightly tedious first. He back-calculated their orbits to remove the effects of the planets, because Jupiter in particular gives every passing comet a shove and changes its path. What he wanted was the orbit each comet had been on before it arrived, the original orbit, the one it had been carrying for however long it had been out there. Then he plotted them, and they piled up. They did not spread evenly across the range of possible values. They clustered, hard, in a narrow band just barely on the bound side of 0, which meant almost all of these comets were arriving on orbits of very nearly the same enormous size, orbits so large that they were only just held on by the Sun's gravity at all. Oort read that pile-up correctly. He concluded that new long-period comets were falling inward from distances of roughly 50,000 to 150,000 astronomical units. He concluded that the Sun must therefore be surrounded by a general cloud of comets with a radius of that order, and he estimated it contained something like 100 billion objects large enough to be observed. He was working with 19 data points. He had no image of a single one of the objects he was describing. He had never seen anything at that distance, nor had anyone, nor would anyone for the next 76 years and counting. And from a table on a page he correctly identified the existence, the approximate size, the geometry, and the rough population of a structure so far away that light takes a year and a half to cross it. It is worth remembering what the world looked like around that piece of paper. 1950 was 5 years after the end of the Second World War, in a country that had been occupied for most of it. There were no computers of any consequence. The calculations were done by hand, or with mechanical assistance that would embarrass a pocket calculator. There were no space probes, because there was no space program. The first object of any kind would not reach orbit for another 7 years. Nobody had seen the far side of the moon. Nobody had seen the Earth from outside. And in the middle of all that, working with pencil and paper and a list of comets, somebody correctly described the outer boundary of the solar system. I want to let that sit for a moment, because I think it is the most quietly extraordinary thing in this entire story. We are, as a species, considerably better at working things out than we are at going and looking. That gap between what we can infer and what we can observe is normally invisible to us, because in most of science the two eventually converge. Somebody proposes something, and a decade or a century later somebody photographs it, and the loop closes. Oort proposed this in 1950. 76 years have passed. We have built telescopes in orbit. We have imaged galaxies whose light left them before the Sun existed. We have photographed the shadow of a black hole in another galaxy entirely, and we still have not seen a single object sitting in the Oort Cloud. The loop has not closed. It may not close in your lifetime. There is a structure surrounding everything you have ever known, which we are confident exists, which we can characterize to within about a factor of 10, and which remains as unobserved today as it was on the day the paper was published. Nobody has ever seen it. Now, I should be careful here, because we have never seen it is exactly the kind of sentence that gets misused. It does not mean this is a guess. It is worth being precise about the difference, because the difference is the whole basis of how we know anything at this scale. A guess makes no predictions. Oort's Cloud made several, and made them in advance, and every one of them could have failed. It predicted that long-period comets should arrive from all directions with no preference for the plane of the planets. They do. It predicted that a plot of those comets by orbital size should show a distinct pile-up near the boundary of being unbound. The feature astronomers now simply call the Oort spike. It does. And it predicted that comets falling in for the first time should be different from the ones that have been around before. Pristine, chemically unprocessed, still carrying volatile ices that would have been cooked off by any previous close pass. They are 3 predictions, made from a table of 19 numbers before the evidence existed to test them. All 3 confirmed. Nobody has ever seen an electron either, and nobody thinks that is a problem. There is one more thing about those 19 comets that I find quietly unsettling, and it is a point about sampling rather than about physics. Every one of them was in Oort's table for the same reason. It had gone wrong. A comet only becomes visible to us when something has knocked it off the orbit it had been holding for billions of years and sent it falling inward. The ones we can see are, by definition, the ones that failed to stay where they were. So the entire catalogue of evidence for the Oort Cloud consists of its escapees, a sample selected with perfect and unbreakable bias for being unrepresentative. Imagine trying to describe a city you have never entered using only the people who have left it, and only the ones who left because something went badly wrong. That is the epistemic position we are in, and it is the position we have been in since 1950. But it does leave us in a peculiar position, because if the spike in that graph is the primary evidence for the largest object in the solar system, then the next thing worth understanding is what exactly that spike is, and what it means that our entire knowledge of this place comes from the small number of its residents that happen to fall out of it. The Oort spike is a bump in a graph, and it is the reason we believe in the largest thing in the solar system. I want to describe it properly, because when you understand what the shape of that graph is actually telling you, the whole structure snaps into focus in a way that no diagram of a shell around the Sun ever manages. Picture a long horizontal axis. On the left-hand end, comets that are tightly bound to the Sun, going round on short, well-behaved orbits. As you move rightward, the orbits get longer and looser and more stretched. And at the far right, at the value 0, is the exact boundary between being held and not being held. The dividing line between an object that belongs to the Sun and an object that is leaving forever. Cross 0 into negative values, and you're looking at something that is not in orbit at all, something passing through. Now plot every well-measured long-period comet on that axis, using its original orbit, the orbit it was on before the planets got hold of it during this particular visit. What you get is not a smooth spread, it is a wall. There is a sharp, dense concentration of comets crowded up against the 0 line, sitting just barely on the bound side of it. Astronomers call that concentration the Oort spike, and it corresponds to comets with orbits so enormous that their average distance from the Sun exceeds 10,000 astronomical units. The formal definition is a range of values between 0 and 1/10,000th per astronomical unit, which sounds like nothing and means everything. The comets in that spike are almost certainly making their first ever visit. They are what astronomers call dynamically new. These are objects that formed 4.5 billion years ago, were thrown outward, settled into an enormous slow orbit, and have been sitting out there in the dark ever since, having never once come close enough to the Sun to be warmed, altered, or noticed. And now, for the first time, one of them is here. The size of the orbits in that spike is where the numbers get their teeth. For orbits calculated using gravity alone, the majority of observed spike comets have average distances somewhere between 20,000 and 50,000 astronomical units. The median original orbital energy across observed samples corresponds to roughly 27,300 astronomical units. That is the typical home address of a comet arriving in your sky. 27,000 astronomical units is not a distance, it is a sentence with numbers in it. So let us convert it into something that behaves. 1 light year is about 63,000 astronomical units, so the typical new comet has been sitting, on average, somewhere around 4/10ths of a light year from the Sun, about 1/10th of the distance to the nearest star, and it has been sitting there since before the Earth had a crust you could stand on. Here is the part I did not appreciate for a long time, and it is the reason the spike is such good evidence rather than merely suggestive evidence. The spike is diagnostic because of Jupiter. Every time a comet passes through the inner solar system, the giant planets change its energy. The effect is not random in its consequences. Statistically, it tends to bind the comet more tightly, pulling it in off that barely attached orbit and onto a smaller one, which means a comet can only be in the spike once. After its first pass, Jupiter has quietly rewritten its orbit and moved it leftward on the graph, out of the spike permanently. Jupiter, in other words, is a one-way door, and that has a beautiful consequence. Everything in the spike must be arriving for the first time. The spike is not a population, it is an entrance. What you're looking at in that graph is not a picture of the Oort Cloud, it is a picture of the doorway, an account of how many things have come through it. Which raises the obvious question of how many things are being missed, and the answer to that is genuinely humbling. Start with the fact that a comet is only discoverable when it becomes bright, and it only becomes bright when it comes close enough to the sun for its ices to start sublimating and throwing out gas and dust. Which means we only find the ones that come in close. Any object on an orbit that brings it no nearer than, say, the orbit of Uranus is effectively invisible to us. It could be enormous. There could be millions of them. We would have no way of knowing. Then there is what is sometimes called the Jupiter-Saturn barrier. A very large fraction of incoming long-period comets never make it to the inner solar system at all, because the giant planets deflect them, capture them, or throw them back out on the way in. The comets that reach our sky are the ones that threaded a gap. Every population estimate we have ever made has been made from survivors of that filter. And then there is the fading problem, which is one of those quiet, unresolved issues that rarely makes it into popular accounts. When you count the comets in the spike, and you use standard models to predict how many of them should come back for a second visit and a third, the prediction is badly wrong. Far fewer return than should. Something is happening to comets on their first pass. They are disrupting, fragmenting, exhausting their volatiles, developing an insulating crust, becoming inert and dark, or simply falling apart. Comet West did it in front of us in 1976, splitting into 4 pieces at perihelion. Comet Eason did it in 2013, in full view of a small fleet of solar observatories, live on the internet. That is worth pausing on. An object that had survived intact for 4.5 billion years in the dark, older than every rock on the surface of the Earth, unchanged since before there were planets to be unchanged relative to, came inward once and did not survive the encounter. 4.5 billion years of stability ended by a single afternoon of sunlight. There is one further complication, and it is my favourite, because it means the size of the Oort Cloud depends on how carefully you model rockets. Comets are not passive. When a comet warms, it does not simply glow, it vents. Jets of gas erupt from the sunlit side of the nucleus, and those jets push. They are functionally small, badly aimed thrusters bolted to a mountain of ice, firing whenever the surface happens to catch the light, and rotating with the nucleus as it spins. The effect on the orbit is tiny. It is also not zero. And when you include those non-gravitational forces in the orbital calculations, the inferred original orbits shift. The median drops. Instead of the 20,000 to 50,000 range you get from pure gravity, you find the typical value falling to something below 20,000 astronomical units, significantly smaller than the classical picture. So the apparent size of the outer solar system depends in part on whether you accounted for the exhaust. I find that detail genuinely delightful and also slightly maddening, because it captures the whole epistemic situation of this subject. We are trying to measure the outer boundary of our own solar system by carefully modelling the outgassing behaviour of individual dirty snowballs, one at a time, and the answer moves depending on how well we do it. None of this means the structure is not there. The 3 predictions held. The spike is real, the isotropy is real, the pristine chemistry of new comets is real. What it means is that our knowledge of the outermost region of the solar system rests on a small, badly biased, and physically messy sample, and everyone working on it knows this perfectly well. It is also, for what it is worth, a very old sample. One of the largest homogeneous studies of this problem covers the long-period comets, discovered between 1801 and 2017, a span of more than 2 centuries of continuous sky-watching, from the age of the refracting telescope and the hand-drawn logbook through to automated all-sky surveys. 216 years of humanity looking up, in every observatory ever built, in order to assemble the graph whose shape is our only real evidence for this place, and the sample is still small enough that arguments about individual comets can move the answer. There is reason to think that is about to improve, at least a little. The Vera C. Rubin Observatory in Chile has begun a 10-year survey of the southern sky designed to image the entire visible sky every few nights, and it is expected to increase the known population of long-period comets by a large factor. More comets means a better resolved spike, and a better resolved spike means tighter constraints on where they are coming from. But notice what that improvement consists of. It is more escapees. It is a longer list of the objects that left. Even the best telescope humanity has ever built for this problem is not going to show us a single object sitting where it lives. It is going to show us more things falling out of a place we still cannot look at. So the spike gives us the doorway, and the doorway gives us a distance, and the distance gives us a number that nobody can feel. Which brings us back to the ruler problem, and to the one measuring instrument I have not yet tried on this. The one we are proudest of, the one we launched in 1977, and the one that is currently doing about 1 million miles a day and getting nowhere at all. Voyager 1 is the fastest thing we have ever thrown, and tonight it is going to break as a measuring instrument in front of you. It launched on the 5th of September, 1977. It is currently about 170 times the Earth's distance from the Sun. Some trackers put it a little above 171, and it is moving outward at roughly 17 kilometers every second. NASA renders that as about 1 million miles a day, which is a beautiful piece of writing, because 1 million miles a day sounds like the largest number a machine could possibly be worth. In other units, it is about 42,000 miles an hour. It is roughly 38 times faster than the airliner you have flown in. It covers the distance from the Earth to the Moon in about 6.5 hours. It has been doing this without a break for 49 years. There is something about that speed that people rarely mention, and I think it changes how you should feel about the whole enterprise. We did not give Voyager most of that velocity. Its rocket got it off the Earth and out towards the outer planets, and after that the great majority of the speed it is carrying tonight was taken from Jupiter and Saturn. Stolen, essentially, in a pair of gravitational encounters that borrowed a fractionally tiny amount of orbital energy from each planet and handed it to a spacecraft weighing less than a small car. We did not accelerate it to interstellar velocity. The planets did. Our contribution was the aim. In November of 2026, Voyager 1 is expected to become the first human-made object to be 1 full light day from Earth. That is about 26 billion kilometers. It has taken us the entire space age to put something 1 day of a lifetime away, and it is dying. This is the part that tends to get left out of the celebration. The spacecraft runs on the heat of decaying plutonium, and that heat declines by a few watts every year, on a schedule that has been known and unchangeable since before it launched. Most of the non-essential instruments have already been switched off, one by one, to keep the remaining ones alive. The plasma wave instrument is still returning data. The transmitter runs at about 22 watts, comparable to a dim household bulb, and by the time that signal reaches Earth, it has spread out so thinly that the receiving dishes are collecting something in the region of a 10 billionth of a billionth of a watt. NASA expects the mission to end in the early 2030s. There is a detail about that dying that I think is quietly beautiful. The decline is arithmetic. The plutonium loses roughly 4 watts of output every year, and it has done so with complete indifference since 1977, which means the end date of the most successful exploration mission in history has been calculable to within a few years for the whole of its life. Nobody had to wait to find out. The engineers who launched it knew, in 1977, roughly when it would stop talking. They built it anyway, and they built into it a set of instructions and images on a gold-plated record with a projected physical integrity of about 1 billion years. A design lifespan chosen not for the mission but for the journey, because the journey was always going to be measured on a scale the mission could not reach. The other thing worth knowing is that the round trip is now about 2 days. Send a command to Voyager 1 tonight and the answer arrives the day after tomorrow. That is not a delay caused by any equipment. That is simply the shape of the distance converted into a working inconvenience. Every conversation humanity has with its most distant object is a conversation with a 2-day pause in the middle of it, and this is the object that has covered 1/700th of tonight's journey. Now let us use it as a ruler. At about 3.5 astronomical units per year, Voyager 1 will reach the inner edge of the Oort Cloud in roughly 300 years. That is NASA's own figure, stated plainly on their public pages. It will not enter the Oort Cloud for about 300 years. 300 years from now is the 23rd century. Every institution that built this spacecraft will have changed beyond recognition or ceased to exist. The languages currently spoken on Earth will have drifted. Every person alive tonight will have been dead for 2 centuries, and the spacecraft will have been cold, silent and unpowered for roughly 270 of those 300 years before it gets to the near edge of the thing we're discussing. Then it crosses. And NASA gives that figure too. It will not exit the outer edge for maybe 30,000 years. Let me put down some markers along 30,000 years, because the number is too smooth to feel. 30,000 years ago, the last Neanderthals were alive somewhere in Europe. The oldest cave paintings we know of had recently been made. The last glacial maximum had not yet happened. Agriculture was 20,000 years in the future. Writing was 25,000 years in the future. Every civilization, every empire, every language, every religion, every war, every piece of music, all of it fits inside the second half of Voyager's crossing. I want you to be somewhere with me for a moment. It is the year 2326. The spacecraft has been dead for very nearly 300 years. Its plutonium has cooled to the point where there is not enough heat to run anything at all, and there has not been for a long time. The 3.7-meter dish is still pointed roughly back the way it came, because nothing has touched it and nothing out here corrodes. The golden record is bolted to the side, uncorroded, unplayed, its cover diagram still perfectly legible to anyone who might ever be in a position to read it. The temperature of the metal is a few degrees above absolute zero, and at this exact moment, by the best estimates anyone ever made, the spacecraft crosses into the Oort Cloud. Nothing happens, there is no boundary, there is no sound, obviously, but there is also no change in anything a sensor would have registered if a sensor had still been running. The particle density does not shift, the magnetic field does not shift, the darkness does not deepen or lighten. The nearest icy body may be several times further away than Saturn is from the Sun, and it is unlit and unimaginably faint, and even if the cameras had power they would see nothing. Behind the spacecraft the Sun is a very bright star. Not a disk, a star. And it has 29,700 more years of exactly this to go. That is what 1,000,000 miles a day buys you. I should mention the others, briefly, because they do not improve the picture. Voyager 2 launched first in August of 1977 and crossed the heliopause in 2018 and travelled slightly slower. Pioneers 10 and 11 have been silent since 2003 and 1995 respectively, and are now essentially archaeological objects drifting outward on their own. New Horizons, the most recent and most modern of them, passed Pluto in 2015, and a small body called Arakoth on New Year's Day of 2019, and is currently somewhere past 60 astronomical units. It is expected to run out of usable power in the 2040s, at somewhere around 90. It is also worth saying that Voyager 1 is not aimed anywhere. It has no destination, and never did. The nearest thing it has to one is a star called Gliese 445 in the constellation Camelopardalis, which it will pass within about 1.5 light years of in roughly 40,000 years, and by then, of course, it will still be inside the region we are discussing tonight for most of the trip. Add them all together. Every spacecraft humanity has ever launched, every kilometre any of them has ever covered, all of it summed. The total is less than 1/200th of 1% of the distance to the outer edge of the Oort Cloud. And if you wanted to do better, if you wanted to actually cross this thing within a single human lifetime, say within 80 years, the arithmetic tells you exactly what you would need. About 1,250 astronomical units per year, roughly 360 times Voyager's speed, something in the region of 2% of the speed of light. We do not have that. We do not have anything remotely resembling that, and we do not have a credible engineering path to it. The fastest object we have ever built is slower than the requirement by a factor of several hundred, and it took the gravity of 2 planets to get it even that fast. So the spacecraft ruler has broken as well. Miles broke immediately, the astronomical unit broke at a few thousand, light time held its accuracy and gave us 18 months, and Voyager, our proudest object, hands back a number measured in geological epochs, which leaves the question of what is actually out there waiting for it. Because I have been describing this place as a shell full of objects, and I have been using words like trillions, and I want to now be very specific about what a trillion objects spread over a distance like that actually looks like. It is not what you are picturing. It is almost exactly the opposite of what you are picturing. When I say the Oort Cloud contains trillions of objects, you have just built a picture, and I need to take it away from you. The picture is a swarm. It is a dense shell of tumbling ice. thick enough that a spacecraft would have to pick its way through, glinting faintly in whatever light reaches it. It is the asteroid field from every film you've ever seen. It is crowded. It is not crowded. It is the emptiest place we know of, and the reason it is empty is precisely because it is so full, because the numbers involved are so large that they have to be spread across a volume that defeats them. Start with what the population estimates actually say. NASA's own language is that there may be hundreds of billions, even trillions, of icy bodies out there. The research literature broadly agrees. Models typically give trillions of objects larger than 1 kilometre across and billions larger than 20 kilometres. One well-known analysis from 1982 put the population of comets brighter than a certain standard threshold at about 1.4 trillion. Oort's original guess of 100 billion looks, from here, distinctly conservative. So, trillions of individual worlds of ice, each one a mountain, each one older than the Earth's oldest surviving rock. Now weigh them. This is where the story goes somewhere I did not expect the first time I read it properly. A paper published in 1983 titled simply The Mass of the Oort Cloud put the total at roughly 1.9 times the mass of the Earth, with the author noting honestly that the uncertainty on that figure was about an order of magnitude in either direction. Later modelling work has produced higher numbers in the region of 7 to 8 Earth masses. The working range you will find quoted in review articles today is something like 1 to 10 Earth masses. Set that against Jupiter, which is 318 Earth masses. The largest structure in the solar system, a shell whose radius may be 100,000 times the Earth's orbit, containing more individual objects than every asteroid, moon, planet, and dwarf planet combined by an enormous margin, may weigh less than 3% of one planet. Possibly less than 1%. You could take the entire outer boundary of the solar system, every object in it, all trillion or more of them, and you would not have enough material to build a second Saturn. The reason is the volume, and the volume is where this stops being arithmetic and starts being something you can feel. Take a shell running from 20,000 out to 50,000 astronomical units, a fairly standard working region for the outer cloud. The volume of that shell is somewhere around 500 trillion cubic astronomical units. Put a trillion objects in it. Distribute them evenly, which is a simplification but a useful one. You get roughly one object per 500 cubic astronomical units, which means the typical distance from one icy body to its nearest neighbour is on the order of 10 astronomical units. 10 astronomical units. The distance from the Sun to Saturn. That is the gap between one object and the next. I want to be careful and say plainly that this is a model-dependent estimate rather than a measurement. The population and the boundaries both carry large uncertainties, and different assumptions move the number around. But the qualitative conclusion is completely robust and entirely standard. The objects out there are separated by distances comparable to the whole span of the planetary system. So here is where you actually are. You're standing on one of them. It is perhaps 5 kilometers across, which means the horizon is very close, a few hundred meters away, curving down sharply, the way the ground curves on a small asteroid. The surface under your feet is water ice mixed with frozen carbon monoxide and methane, and a great deal of dark dust, and it is one of the blackest surfaces in the solar system. Cometary nuclei typically reflect about 4% of the light that falls on them. That is darker than fresh asphalt. You would be standing on something closer to charcoal than to snow. The temperature is a few degrees above absolute zero. Not cold in the way a winter night is cold. Cold in the way that means nothing has ever happened here. The volatile ices under your boots have never sublimated, not once in 4.5 billion years, because nothing has ever been warm enough to make them. This object is a piece of the material the solar system was assembled from, preserved exactly, because it was thrown somewhere and nothing could reach it. You are moving. You're in orbit around the Sun. But at this distance, the orbital speed is something like 100 meters per second, slower than a small aircraft, and there is no reference point of any kind against which to notice it. The stars do not shift. Nothing passes. Your orbital period is around 11 million years, which means that in an entire human lifetime you would complete about 100,000th of one lap, and you are barely attached. This is one of the strangest physical facts about the region, and it becomes obvious the moment you do the arithmetic. Out at 100,000 astronomical units, the speed you would need to escape the Sun entirely is about 130 meters per second. That is roughly 300 miles an hour. It is slower than a light aircraft. Everything out here, trillions of objects, 4.5 billion years of stability, the entire outer boundary of the solar system, is held in place by a grip so weak that a nudge you could deliver with a decent rocket engine would send an object off into the galaxy, and it would never come back. It is also not all ice. The default picture of the Oort Cloud is a comet reservoir, and that is mostly right. But one study published in the monthly notices of the Royal Astronomical Society estimated a population of something like 8 billion rocky asteroids out there as well, objects scattered outward from much closer in, from the same violent early sorting that threw everything else away. And when you divide the estimated total mass across the estimated population, the average object comes out somewhere in the region of a small mountain, a body a few kilometers across weighing perhaps 1,000 billion tons, trillions of small mountains, each one alone. Now look for your neighbour. There is one. There are trillions. Statistically, the nearest is out there in some direction, about as far away as Saturn is from the Sun, and it is a mountain of black ice with no light source anywhere near it. You cannot see it. There is no instrument you could carry that would let you see it. If you stood here for the entire 11 million year orbit, nothing would ever pass close enough to appear as anything other than a star, and almost certainly nothing would pass close enough to appear as anything at all. And that is the thing I keep coming back to. We have found a place that contains more individual worlds than everything else the Sun holds put together, trillions of them, and every single one of them has spent the entire history of the solar system utterly alone. Not one of them has ever had a neighbour close enough to see. Not one of them has ever been visited by another. They were thrown out there 4.5 billion years ago. They arrived in the dark, they slowed almost to a stop, and they have been sitting there ever since with a Saturn's worth of nothing on every side. It is the most populous region in the solar system, and it is the loneliest place in it, and those two facts are not in tension. They are the same fact viewed from two different distances. This, I think, is what far actually means, once you get past the arithmetic. Far is not a large number. Far is the condition where the number of things stops helping. You can pack 1 trillion objects into a volume and produce something emptier than any vacuum chamber ever built on Earth, and the trillion does not save you. It never even comes up. If you want a physical model you can hold, try this one. Shrink the Sun to a grain of sand 1 millimeter across and set it on a table in front of you. On that scale, the Earth is about 10 centimeters away, the width of your hand. Neptune is about 3 meters away, across the room. Voyager 1, after 49 years of continuous flight at 1 million miles a day, is roughly 17 meters away, out in the corridor, and the outer edge of the Oort Cloud is 10 kilometers away. You would have to leave the building, leave the street, and travel for the better part of a morning to reach it, while the Sun sits on your table as a single grain of sand. Which is also, incidentally, why we have never seen it. There is nothing out there dense enough to block a star, bright enough to reflect anything, or warm enough to glow. The thing is not hidden. It is simply so thinly spread that there is nothing for any instrument to catch. And we are only about halfway through what is out there, because everything I have described so far is the outer cloud. There is another one underneath it, closer, denser, and even less observed. And the reason we think it exists is that without it, the thing I have just described to you should have been stripped away and lost a very long time ago. Before we go looking for that inner cloud, let us stop for a moment and put down everything we are carrying. We are about halfway through tonight, and if you have drifted in and out, which is entirely the point of this channel and requires no apology from anybody, this is the part where I catch you up. And if you have been awake for all of it, this is still worth doing, because the pieces we have collected so far turn out to fit together into a shape that is not obvious until you set them side by side. Here is what we have. We started with a diagram. The solar system as everyone learns it. A sun, 8 planets, a boundary somewhere just past Neptune, and the edge of the page. And we established that the diagram is not a simplification of the solar system so much as a picture of a very small piece of it, and that the actual outermost region is something called the Oort Cloud, which nobody has ever seen. Then we took the measuring instruments out one at a time and watched them fail. Miles failed instantly, because miles are a walking unit, and this is not a walk. The astronomical unit, the honest human-anchored distance from the Earth to the Sun, carried us comfortably out past Neptune at 30, and then collapsed the moment we asked it to express 100,000. Light was next, and light did something worse than fail. Light stayed perfectly accurate. It gave us the ladder. 8 minutes to Earth, 4.5 hours to Neptune, 7.5 hours past the Kuiper Belt, and 17 hours to the heliopause, which is the whole of the human reach, everything we have ever built or touched or photographed, sitting inside a single day of light time. And then that same particle of light continued for 10 to 28 more days before reaching the inner edge of the Oort Cloud, and for something like 18 months before it was finally past the outer one. The tool we used to make distance feel friendly told us the number, and the number was worse. Then we went back to 1950, and to Jan Oort, and to 19 comets, and we found that the entire basis for believing in this place is a table of numbers and the shape they make when you plot them. A spike, crowded up against the boundary between being held by the sun and being free of it, made of objects arriving from 20 to 50,000 astronomical units out, most of them on their first and only visit. We found that Jupiter acts as a one-way door that lets each comet into the spike exactly once, and we found that our entire sample consists of escapees, the objects that failed to stay where they were. Then we tried Voyager, 1 million miles a day, 49 years of continuous flight, and a set of answers measured in centuries and geological epochs. 300 years to the near edge, 30,000 years to cross, and a spacecraft that will have been dead for 270 years before it arrives. And then we went out and stood on one of these objects. 5 kilometers of black ice at a few degrees above absolute zero, orbiting so slowly that a lifetime buys you 100,000th of a lap, held on by a grip so weak that 300 miles an hour would break it. Trillions of them, and the nearest one to you as far away as Saturn is from the Sun, invisible, and always has been. So that is the shape of it. A structure we cannot see, made of objects we cannot detect, at a distance that breaks every ruler we own, known entirely through the small unrepresentative fraction of its members that fell out of it. And I have still not told you how far away it is. I know. I said at the beginning that I would not, and I meant it, and we are now halfway through, and I have given you ranges and ladders and comparisons and no answer. That is deliberate, and it is not a trick. The reason is that the answer to how far is the Oort Cloud is not a number, and if I give you a number now you will take it and stop, and you will miss the actual thing. But there is also a second reason, and it is more honest and more interesting than the first, and I have been circling it all night without saying it directly. We do not know, not in the way that phrase is usually meant, where a scientist says, "We do not know," and means, "We know it to 3 decimal places and are arguing about the 4th. I mean it flatly. Look at what NASA publishes on its own fact page for this region, and you will find, in the same document, that the inner edge is between 2,000 and 5,000 astronomical units, that the outer edge is between 10,000 and 100,000, and that the region as a whole occupies 5,000 to 100,000. That is not a measurement with error bars. That is a factor of 10. Now think about where else in science you would tolerate that. We know the age of the universe to within about 1%. We know the mass of an electron to 11 significant figures. We have measured the distance to galaxies whose light left them when the universe was 1/20th of its current age. And the outer boundary of the solar system we live in, the one structure we are actually inside of, is a quantity we cannot pin down to better than 1 order of magnitude. The mass has the same problem, 1 to 10 Earth masses. The population has the same problem, 100 billion to more than 1 trillion. Every headline number about this place is uncertain by a factor of about 10, and that uncertainty has not meaningfully improved since the 1950s. That is not a failure of effort. It is a consequence of the thing itself, and by the end of tonight you will see exactly why the factor of 10 is not going away, and why, in a sense I will explain properly at the end, it is not even the right kind of question to be precise about. So let me tell you what is left, because there are 3 more pieces, and each one changes the question rather than answering it. The first is physical. We have never seen this place, but pieces of it have come to us, and some of them have been photographed, tracked and measured in detail. There is an object out there 137 kilometers across whose orbit takes it 40,000 astronomical units from the Sun and back once every 3 million years, and we know where it has been. That is coming next. The second is structural. Everything I have described so far is the outer cloud. There is very good reason to think there is another one underneath it, closer in, denser, holding possibly tens or hundreds of times as many objects, and the argument for its existence is not a hunch. It is a necessity. Without it, the outer cloud should have been stripped away and scattered into the galaxy long ago, and the fact that we still have comets is the evidence that something has been quietly refilling the shelf for 4.5 billion years. And the third is the one that reframes the whole thing, and it is the reason I have been so stubborn about not giving you a number. The outer edge of the Oort cloud is not defined by where the objects stop. It is defined by something else entirely, by a competition running continuously for the age of the solar system between the Sun and the rest of the galaxy. And that competition has visitors. Something walked through the outer shell of our solar system 70,000 years ago, while human beings were alive and looking up, and something else is coming in about 1.25 million years, and it will come closer. So we have covered the distance. What is left is the ownership. Nobody has ever seen the Oort cloud, but we have held pieces of it in the field of view of a telescope and photographed them and watched one of them come apart. That is the shift I want to make in this part, because so far tonight the Oort cloud has been an inference, a shape derived from a graph, a distance derived from a shape. It has had no body, and it does have a body. Every long-period comet that any human being has ever stood outside and looked at was a piece of that shell, dislodged and falling, and the thing they were actually seeing was distance made visible. Let me start with the biggest one we have found. In 2021, astronomers announced an object catalogued as C2014 UN271, and named for the two people who found it in the data, Bernardinelli and Bernstein. It had been sitting, unrecognized, in archival images from the Dark Energy Survey, which is worth noting on its own. The largest comet nucleus ever discovered was in a database for years before anybody looked at it properly. The limiting factor was not the telescope, it was attention. When it was found, it was about 29 astronomical units from the Sun. That is further out than Neptune. No Oort cloud comet had ever been detected that far away, because at 29 astronomical units, a comet is normally a cold, inert lump, and this one was already active, already venting, already surrounded by a faint haze of gas and dust, already being warmed into visibility at a distance where the Sun is a bright star rather than a disk. Then Hubble measured the nucleus. It came out at roughly 137 kilometers across, with published estimates clustering between about 119 and 137 kilometers. That makes it the largest cometary nucleus ever measured, by a wide margin, a body 80 miles across, larger than the state of Rhode Island, about 50 times the size of a typical comet nucleus. Its estimated mass is 500 trillion tons, roughly 100,000 times that of an ordinary comet, and its own gravity, faint as it is enough to make it very nearly round. And it is, in the words of one of the astronomers who measured it, blacker than coal. And here is where it came from. Its previous aphelion, the furthest point of its last orbit, was 40,400 astronomical units, measured to within a couple of hundred. That is not an estimate for a population. That is a specific number for a specific object. 40,400 astronomical units is about 2/3 of a light year. Its orbit is inclined at about 95 degrees, almost exactly perpendicular to the plane of the planets. It does not go round the way anything else goes round. It comes down through the solar system from above, at right angles, which is precisely the signature Oort predicted for objects arriving from a spherical shell rather than a flat disk. The orbital period is roughly 3 million years. Take a moment with that. 3 million years ago, the last time this object was in our part of the solar system, Australopithecus was walking in East Africa. There were no humans, there was no genus Homo, and even then it did not come close. Reconstructions of its previous passage put its nearest approach to the Sun at about 18 astronomical units, out past Uranus. It has never been anywhere near us. It will not come near us this time either. Its perihelion, in 2031, will keep it out at about 11 astronomical units, roughly the orbit of Saturn. So the largest comet we have ever found spends essentially the whole of every orbit somewhere we cannot see, comes in once every 3 million years, does not come close, and we happen to catch it. Backwards integration of its path, modelling the pull of the galaxy and the known passages of nearby stars, suggests it is a pristine object, dynamically new, arriving genuinely for the first time in the sense that matters. We found it because it was enormous and because we got lucky. There is no reason to think it is unique. There is every reason to think there are many more like it, and that we have seen essentially none of them. now the ones you may have actually looked at. Comet Hale-Bopp in 1996 and 97 was visible to the naked eye for about 18 months, a record. If you were alive and outdoors in the Northern Hemisphere in the spring of 1997, you saw a piece of the Oort Cloud. Its nucleus is estimated at somewhere between 40 and 80 kilometers, and it did something that demonstrates in a single apparition the exact mechanism we discussed earlier. On its way through, the planet's changed its orbit. It arrived on a path with a period of roughly 4,200 years and left on one of about 2,500. Jupiter took a bite of its orbital energy, the way it does to everything, and the comet will now come back sooner than it was going to. It has moved leftward on the graph. It is out of the spike permanently. Comet Hyakutake in March of 1996 passed within a tenth of an astronomical unit of the Earth. The Ulysses spacecraft, entirely by accident, flew through its tail and found that the tail extended more than 3.8 astronomical units. That is longer than the distance from the Sun to the asteroid belt, a comet nucleus of a few kilometers, producing a structure longer than the inner solar system. Comet Siding Spring in October of 2014 passed extraordinarily close to Mars, close enough that NASA moved its orbiting spacecraft around to the far side of the planet to shelter them from the dust. It survived the encounter. It deposited a measurable layer of cometary material in the Martian atmosphere and temporarily created a new layer in the planet's ionosphere. An object from the outer edge of the solar system physically altered the atmosphere of a planet, and we watched it happen. It will not be back for about 740,000 years. And Comet Ison, which we have already touched on, did not survive its encounter at all. There is a line on NASA's public page about this region that I have not been able to stop thinking about since I first read it. They note that most known long-period comets have been seen exactly once in recorded history, because their orbital periods are so long, and then they add that some have orbits so long that the last time they passed through the inner solar system, our species did not yet exist, and that others have never come close to the Sun at all in the billions of years since they formed. Others have never come close to the Sun. Not once. Not in 4.5 billion years. So when we look at comets, we are not looking at the Oort Cloud. We are looking at its casualties. Every object in every catalogue is one that something went wrong for, one that got nudged 4.5 billion years into a stable arrangement and started falling. The ones that are fine are the ones we will never see, which brings the sentence back around, and this time it means something different from the way it meant it in the first minutes of tonight. Nobody has ever seen it, but we have measured a piece of it 137 kilometers across. We have watched one of its members lose its atmosphere against the Sun on a live feed. We have flown a spacecraft through the tail of another and measured it out past the asteroid belt. We have had one of them change the sky of Mars. The place is invisible and its residents are occasionally spectacular. There is one more thing worth saying about them, and it is a small physical detail that has a strange effect on how you picture all of this. Cometary nuclei are among the darkest objects in the solar system. Typical reflectivity is around 4%, darker than fresh asphalt, closer to charcoal than to ice. The brightest transient objects in the sky, the ones that stopped populations in their tracks throughout history, the ones recorded in chronicles and in scripture and stitched into medieval embroidery, are produced by some of the blackest surfaces the Sun has ever shone on. What you see when you see a comet is not the object. It is the object's exhaust, lit up. There is a second detail of the same kind, and it took people a surprisingly long time to work out. A comet's tail does not stream behind it like the wake of a boat. It points away from the Sun, always, regardless of which way the comet is travelling, which means that on the outbound leg of its journey, a comet flies tail first, with its own tail out in front of it. Kepler noticed this in the 17th century, and it was the first real evidence anyone had that something is streaming continuously outward from the Sun. 4 centuries before we measured the solar wind directly, comets were showing us it was there, and even Halley, the most famous comet in human history, the one that comes back every 76 years, the one people plan their lives around seeing twice, is not from tonight's region at all. It is a short-period comet from the disk from much closer in. The comets we know best are precisely the ones that do not come from the place we're talking about, but there is one object that might. One object we have actually found, and photographed, and named, which appears to belong not to the Kuiper belt and not quite to the Oort Cloud, but to a structure between them that nobody has ever confirmed exists. In November of 2003, Astronomers working at Palomar Observatory found a moving point of light, and it did not fit anywhere. They named it Sedna, after the Inuit goddess of the sea, who according to the tradition lives in the cold depths of the Arctic Ocean. It was a deliberate choice. Whoever picked it understood what they were naming. Sedna is about 1,000 kilometers across, which puts it in the range of a small dwarf planet. Its surface is among the reddest in the solar system, comparable to Mars in color. The result, we think, of billions of years of radiation slowly cooking the surface ices into complex dark organic compounds. It is not a comet. It is a world, and its orbit is the strangest of any large body then known, and remains one of the strangest known now. At its closest approach to the Sun, it is about 76 astronomical units out. At its furthest, it is about 937. One lap takes roughly 11,400 years. Look at that closest approach again, because it is the whole point. 76 astronomical units. Neptune orbits at 30. Sedna never comes anywhere near it. It stays more than twice Neptune's distance, even at its nearest, which means Neptune cannot reach it. Not now, and not ever. The gravitational sorting that put most distant objects where they are, the scattering by the giant planets that built the Kuiper Belt and the scattered disk and threw everything else outward, cannot have put Sedna on this orbit. Neptune is not capable of it, and yet its furthest point, at 937 astronomical units, is nowhere near the classical Oort Cloud either. It does not even reach the near edge of the inner boundary range. It is not an Oort Cloud object in the sense we have been using all night, so Sedna sits in a gap, too far out to have been placed there by the planets, too close in to be part of the shell. Something put it there, and it was not any process we can currently point to happening. The proposed explanations are all interesting and none of them is confirmed. A close passage by another star during the Sun's earliest years could have lifted it. It could have been captured outright from another star's disk. A distant undiscovered planet could have shepherded it. Or it may be a leftover from the crowded environment the Sun was born into, when other stars passed far closer than any star does now. Take your pick. Nobody can currently distinguish between them. But the reading that matters for tonight is the dynamical one, and some astronomers have made it explicitly. Sedna may be the first known member of the inner Oort Cloud. Then, in 2014, Trujillo and Shepard announced another one, an object called 2012 VP113, with a perihelion of about 80 astronomical units. Same category, same problem. And that changed things, because one strange object is an anomaly, and two strange objects with the same strangeness is a population. Their paper put it directly. These objects may be members of an inner Oort cloud, whose population could outnumber all other dynamically stable populations in the solar system. Read that again slowly. A population we have two confirmed members of might contain more objects than every asteroid, every Kuiper Belt body, every moon, and every planet put together. There is a further detail in Sedna's orbit that supports the reading, and it is a subtle one. True outer Oort cloud objects arrive at every possible inclination. That isotropy is the founding observation of the whole subject. Sedna does not. Its orbit is tilted only modestly relative to the plane of the planets, roughly in line with the Kuiper Belt and the planetary disk, which is exactly what you would expect if the inner cloud is a structure that still remembers, faintly, the flat disk it was thrown out of before the galaxy had time to stir it into a sphere. The inner cloud may be the halfway stage of a process we are watching frozen in place. The same paper that announced the second object also noted something else, almost in passing, that has since generated an enormous amount of work. The most distant known objects appear to have their orbits clustered in a way that would not happen by chance. That observation is the seed from which every modern distant planet hypothesis grew. It is not settled. The statistics are argued over, and it is a different question from tonight's. But it is worth knowing that the first firm evidence for the inner Oort cloud, and the first firm evidence for something unexplained shepherding the outer solar system, arrived in the same announcement. Now, that inner cloud is not a new idea invented to accommodate Sedna. It had a name and a date long before Sedna was found. In 1981, an astronomer named Jack Hills at Los Alamos proposed it, and it has been called the Hills Cloud ever since. It runs, in most models, from roughly 2,000 to 3,000 astronomical units out to perhaps 10 or 20,000, sitting underneath the outer cloud, between it and the scattered disk, and models consistently predict that it is far denser, tens of times, in some treatments hundreds of times, as many cometary nuclei as the outer cloud contains. Here is why Hills proposed it, and this is the argument I find genuinely elegant. We established earlier that the outer Oort cloud is barely attached. At those distances, the sun's grip is so weak that escape velocity is a few hundred miles an hour, and an object needs only a small nudge to be thrown into the inner solar system or lost to the galaxy entirely. Passing stars nudge them. The tidal field of the Milky Way nudges them, continuously, for the entire age of the solar system. Run that forward for 4.5 billion years and you get a problem. The outer cloud should have been stripped, not partially, substantially. Given the rate at which stars pass and the persistence of the galactic tide, a shell that weakly bound should have been picked apart and dispersed long ago, and we should not be seeing long-period comets today at anything like the rate we do. But we are. Comets keep arriving. New ones, pristine ones, first-timers, arriving in the spike, this century, this decade, this year. So something is refilling the shelf. That is the argument for the Hills cloud, and it is not an argument from observation. It is an argument from persistence. The inner cloud is denser and more tightly bound, which means it survives the stripping, and over billions of years it slowly feeds objects outward, replacing what the galaxy takes, keeping the outer cloud stocked. It is a reservoir behind a reservoir, which means the reason we still have comets, the reason there was anything for Jan Oort to plot in 1950, the reason any human being has ever looked up and seen one, is a structure that has never been directly detected, whose existence we infer from the fact that a different structure we have also never seen has not yet been destroyed. And we know of maybe 2 objects that might belong to it. I want to add one thing about Sedna specifically, because it is a detail about detection rather than about physics, and it should make you uneasy in a useful way. For the overwhelming majority of its 11,400-year orbit, Sedna is far too faint for any telescope we have to see. We can only detect it during the relatively brief window when it is near the closest point of its path, and we found it in 2003, which means we caught it during that window, a window that lasts a few centuries out of 11 millennia. Think about what that implies. If a 1,000-kilometre world is only visible for a small fraction of its orbit, and we happen to find one during its visible phase, then the number of similar objects currently out there in the invisible phase of their own orbits is not small. It is very large. There is no reason at all to think Sedna is rare. There is every reason to think it is simply the one that happened to be near enough to catch when we were looking. It is also the reason that occasional mission concepts to Sedna focus so tightly on a narrow window. A spacecraft aimed at it has to catch it near perihelion, because if you miss, the target recedes to 937 astronomical units, nearly 8 times further out than the heliopause, and the mission stops being difficult and starts being impossible. There may be hundreds of Sednas, there may be thousands. They are out there right now, in the dark part of their orbits, and no instrument on Earth or in orbit could find a single one of them tonight. So the picture has now grown downward as well as outward. There is the outer cloud, unseen. There is an inner cloud beneath it, denser, also unseen, and necessary. And there is a class of large worlds in between, of which we have found 2 and expect many. And we still have not answered the question, because I have still not told you what actually sets the edge. Everything so far has been about what is out there. The last piece is about who it belongs to, and the answer is not entirely the Sun. The Sun does not own the outer edge of the solar system outright, and this is the part of tonight where that stops being a poetic way of speaking and becomes a specific, calculable statement about gravity. Every body with mass has a region around it inside which its gravity is the one that matters. Astronomers call it the Hill sphere. Inside that boundary, a smaller object orbits the body. Outside it, the body's pull is overwhelmed by something larger, and the object goes off and orbits that instead. The Earth has one. It is why the Moon orbits us rather than being taken by the Sun. The Sun has one too, and the thing on the other side of the argument is the Milky Way. The Sun's Hill sphere is usually quoted at somewhere around 100,000 astronomical units, roughly 1.5 to 2 light-years, depending on the assumptions you use for the local mass of the galaxy. Look at where that falls. It is the same number as the outer edge of the Oort cloud. NASA puts the same idea in a way that is easier to picture. They describe the Oort cloud as extending perhaps 1/4 to halfway from our Sun to the next star. The next star is Proxima Centauri, 4.2 light-years away. So on the outer estimate, the Sun's territory reaches out to something like the halfway line. and there is nothing at all on the far side of that line except the point at which some other star's territory begins. That is not a coincidence, and it is the single most important structural fact in this entire subject. The Oort Cloud does not end at 100,000 astronomical units, because the Sun ran out of icy bodies to throw. It ends there because that is where the Sun stops winning. Anything further out is not held. It drifts, and it goes, and it becomes the galaxies. The outer boundary of the solar system is not a place where matter stops. It is the surface at which one gravitational claim gives way to another, and it has been sitting there, being negotiated for 4.5 billion years. I want to explain what does the negotiating because it has a name and it is not a metaphor. The galactic tide is exactly the same phenomenon as an ocean tide, scaled up until it applies to a solar system. Tides arise from difference, not from the strength of a gravitational pull, but from the fact that the pull is slightly stronger on the near side of an object than the far side. The moon does not lift the ocean, it lifts one side of the Earth marginally more than the other, and the difference sloshes. Now apply that to the Sun and the Milky Way. The galaxy pulls on the Sun. It also pulls on an icy body 100,000 astronomical units from the Sun. And those two pulls are not identical, because the two objects are not in the same place. Across the span of the Oort Cloud, 1.5 light years, the galaxy's pull varies enough to matter. Slowly, patiently, over millions of years, that difference torques cometary orbits, raising some perihelia, lowering others, quietly reshaping the whole shell. That is the mechanism, and its consequence is the reason you have ever seen a comet. An object sitting at 30,000 astronomical units with a perihelion far outside the planetary region is safe. It goes round for millions of years, untouched. But the galactic tide slowly lowers that perihelion and lowers it again over many orbits, until one pass takes the object close enough to the Sun to warm, and it lights up, and someone on Earth sees it, and it goes into a catalogue. The tide is not a disturbance to the system. It is the delivery mechanism. NASA identifies it as likely the strongest single influence in shaping the Oort Cloud in the first place, back when the giant planets were throwing material outward, and something had to lift those orbits out of the planet's reach and park them. The galaxy built this structure as much as the Sun did. It is worth telling the formation story properly here, because it only makes sense once you know about the tide, and it changes what the Oort Cloud is. When the planets finished assembling, about 4.6 billion years ago, the region they formed in was still littered with leftovers, icy planetesimals, chunks of the same material the planets were built from, in enormous numbers. And the giant planets, Jupiter above all, began throwing them. Some were thrown clean out of the solar system, never to return. Others were thrown onto orbits so stretched that they went out to tens of thousands of astronomical units, and then came back. And coming back is the problem, because an object that comes back can be thrown again and eventually ejected. On its own, that process does not build a cloud. It builds a slowly emptying solar system. What made the difference was the galaxy. Once those objects reached far enough out, the tidal field began to act on them, and it lifted the closest points of their orbits away from the planetary region. The objects stopped coming back. They were, in effect, taken out of Jupiter's reach and parked. So the Oort Cloud is not native to the outer solar system. Every object in it formed close in, near where the planets are, out of the same material as the planets. It was thrown out by the giant planets and caught by the Milky Way. The outermost region of the solar system is made entirely of the inner solar system evicted, and the eviction was only permanent because the galaxy intervened. There is a consequence to that which is easy to miss. The Sun and the galaxy did not merely compete for this material, they collaborated on it. Neither one alone would have produced an Oort Cloud. It required a star violent enough to throw and a galaxy patient enough to catch. And the Sun is not stationary while this happens. It is in orbit around the centre of the Milky Way, completing one circuit roughly every 230 million years. Since the Oort Cloud formed, the Sun has carried it around the galaxy about 20 times. That is a strange thing to picture. This shell, 100,000 astronomical units across, a light-and-a-half-year sphere of black ice, trillions of objects, none of them able to see any other, is not sitting still. It is being dragged in a circle at about 230 kilometers per second, through different regions of the galaxy, past different densities of stars, through the spiral arms and out again, for 20 complete laps. And the tidal field it experiences changes as it goes. There is a further wrinkle. The Sun does not orbit the galaxy in a flat circle. It bobs, oscillating up through the plane of the galactic disk and back down again, roughly every 30 million years or so. As it does, the strength of the vertical component of the galactic tide changes. Whether that produces a detectable rhythm in the rate at which comets arrive is genuinely argued about, and I would not want to overstate it. But the mechanism is real, and the oscillation is real, and the Oort Cloud has been riding it for the entire history of the Earth. The tide also does not act evenly, which produces a subtle and rather beautiful observational consequence. The galactic tidal field is strongest for orbits oriented in certain directions relative to the galactic plane, and much weaker for others. So the comets it delivers are not perfectly isotropic after all. There is a faint detectable preference in the directions from which long-period comets arrive, and that preference lines up with the geometry of the galaxy rather than the geometry of the solar system, which means that if you plot enough comet arrival directions and look carefully, you can see the Milky Way in the data. Not the light of it, the pull of it, written into the paths of objects falling in from a place we have never seen. So let us restate the boundary properly, because it has changed shape over the last few minutes. Earlier tonight I described the outer edge of the Oort Cloud as a distance we cannot pin down to better than a factor of 10. That was true, and it was also the wrong frame. The reason the number is imprecise is not that our instruments are inadequate. It is that the thing being measured is not a location. It is an outcome. It is where a continuous 4.5 billion year competition between the Sun and the galaxy currently sits. And that outcome is different for different objects, in different orbital orientations, at different points in the Sun's journey around the Milky Way. The solar system does not have an edge. It has a balance of power. And a balance of power is not the kind of thing that has a number. There is one more thing that acts on that balance, and it is not gradual at all. The tide is slow, patient, and permanent, but every so often something arrives that is none of those things. Something comes close enough to reach in and pull, hard, over the span of a few thousand years, and one of those things came through while our species was already here. 70,000 years ago, a star passed through the outer shell of our solar system, and there were people on Earth at the time. I want to say that sentence again in a slightly different way, because the first version sounds like a headline, and the second version is what actually happened. About 70,000 years ago, a binary system, a small red dwarf with a brown dwarf companion, came within roughly 52,000 astronomical units of the Sun. That is about 8/10 of a light year, and a team of astronomers led by Eric Mamajek at the University of Rochester, who reconstructed the encounter from the system's measured velocity and trajectory, put the probability that it passed through the outer Oort Cloud at about 98%. The object has a catalogue designation that is not built for storytelling, WICJ 072003.20-084651.2, so everyone calls it Schultz's star, after the astronomer who identified it. It currently sits about 20 light-years away in the constellation Monoceros, and it is moving away from us, and it will keep moving away. To appreciate how close 8/10 of a light-year is, compare it to the nearest star we have now. Proxima Centauri is 4.2 light-years away. Schultz's star came about 5 times closer than that. No other star is known to have ever approached the solar system so nearly. Now let me put you there, because the thing I want you to feel about this is not the drama. It is the absence of drama. It is 70,000 years ago. Somewhere on a plain, or a coastline, or a ridge, a human being is awake at night. Anatomically, modern humans are alive and widely distributed by this point. Whatever else is true about that person, they have the same eyes you do, and the same capacity to look up and wonder what they are seeing. They look up, and nothing is different. There is no new bright star, there is no comet, there is no light in the sky that was not there the year before. Schultz's star is a red dwarf of about 8% of the Sun's mass, with a brown dwarf beside it of about 6%, which is to say, it is intrinsically very faint. Even at its closest, even at 8/10 of a light-year, the calculations put it at around 10th magnitude. That is roughly 50 times fainter than the dimmest thing the unaided eye can pick out on a dark night. It was, for the entire encounter, completely invisible. There is one exception, and it is a small and lovely one. Red dwarfs are magnetically active and they flare, sometimes brightening by factors of thousands for minutes or hours at a time. So it is genuinely possible that somebody, 70,000 years ago, looked up during one of those flares and saw a faint star appear where there had been nothing, and watched it for a while, and then watched it fade. Nobody would have thought anything of it. Nobody could have. Meanwhile, 52,000 astronomical units out, in a region no human being would conceive of for another 70,000 years, the passage is doing its work. Icy bodies that had been sitting on the same orbits for 4.5 billion years feel a pull from a direction that has never pulled before. The change is not violent. It is a small alteration in velocity, a slight tilt, a perihelion nudged inward by some amount, and then the star is past and moving away, and it will never come back, and nothing happens for 2 million years. That is the part I find hardest to hold. The comets that were disturbed by that passage are still falling. It takes an object at 50,000 astronomical units an enormous span of time to complete even part of a fall inward. The timescales involved mean that any increase in comet flux caused by a stellar encounter arrives at the inner solar system roughly 2 million years afterwards, spread out over a long, slow, indistinct rise rather than a shower. Whatever Schultz's star did to us has not arrived yet. It is in transit. It will get here long after our species has become whatever it is going to become. So the largest thing to happen to our solar system in the entire span of human existence was invisible when it occurred, and its consequences will not be visible until long after everyone who could have witnessed it is gone. It is also worth being precise about that 98% figure, because it is a good example of how this kind of claim is actually made. Nobody watched Schultz's star pass. What the team had was a measurement of where it is now, how fast it is moving, and in what direction, and from that you run the motion backwards. The uncertainty in those measurements propagates backwards too, so instead of a single trajectory you get a spread of possible ones. The team simulated 10,000 orbits for the star, each one consistent with the measurements and with the gravitational field of the galaxy, and counted how many passed inside the outer Oort Cloud. 98% of them did. That is what the number means. And for what it is worth, of those 10,000 simulated passages, exactly one brought the star deep enough to reach the inner cloud, where the effects would have been considerably larger. We very probably got the gentle version. It is not a hedge. It is an honest statement of what the data supports, and it is the same technique that tells us Gliese 710 is coming. I said earlier that the Sun does not entirely own the outer solar system. This is what that looks like in practice. It is not a metaphor about gravity. It is a red dwarf physically moving through the region and taking things with it. And these encounters are not rare on the timescales that govern this place. Stars pass within 100,000 astronomical units of the Sun, something like once every few 100,000 years, on average. The Oort Cloud is not a sealed structure with an occasional intruder. It is stirred, on a regular schedule, as a matter of routine. And it used to be very much worse. The Sun almost certainly did not form alone. Stars are born in clusters, hundreds or thousands of them condensing out of the same cloud, packed close together before drifting apart over tens of millions of years. In that environment, stellar encounters were not once every few 100,000 years events. They were constant, and they were far closer than anything we have experienced since. Simulations of that period suggest the young solar system was being reached into repeatedly by neighbours, at distances that would be unthinkable today, which has an interesting implication for something we discussed earlier. If you want an explanation for how Sedna ended up on an orbit that Neptune cannot produce, and the Oort Cloud does not account for, one of the leading candidates is simply that it was put there during that crowded early period by a star that has long since drifted away and is now somewhere else in the galaxy entirely, unidentifiable, unreachable, and completely anonymous. There may be a specific star out there tonight that is responsible for a specific object in our solar system, and we will never know which one. Which brings us to the one that is still coming. Gliese 710 is a K-type dwarf star, and it is going to come closer than Schultz's star did. Measurements from the Gaia spacecraft, which has determined positions and velocities for more than 1 billion stars, and which turned the question of future stellar encounters from speculation into a catalogue, put its closest approach at about 0.054 parsecs. That is roughly 11,000 astronomical units. The 95% confidence interval places it inside about 17,000. It will happen in about 1.25 to 1.33 million years. 11,000 astronomical units is not a graze. Schultz's star passed through the outer fringe at 52,000. Gliese 710 will pass through the body of the structure, into the region where the outer cloud and the Hills cloud overlap, in the densest part of the whole arrangement, and it is more massive than Schultz's star was, at around 6/10 of the mass of the Sun, which makes it the more significant encounter of the two by a considerable margin despite arriving later. Here is the detail that I think should genuinely unsettle you, and it is not about the star. It is about us. Every time our measurements have improved, Gliese 710 has come closer. The early estimates from before the modern astrometric surveys put its closest approach much further out, tens of thousands of astronomical units with enormous uncertainty. Then the first Gaia data release came in and the distance shrank, then the second and it shrank again, then improved reductions and it shrank further, and the timing shifted slightly later. That is not the star moving. The star has been on this trajectory for millions of years and will remain on it regardless of what we do. That is us, slowly getting the answer right and discovering each time that we'd been comfortably wrong in the same direction. There is a temptation, when you hear about a star passing through the Oort Cloud, to imagine catastrophe, a sky full of comets, an era of bombardment, the sort of thing that turns up in documentaries with a lot of orchestral strings. That is not really what happens, and the truth is stranger for being so slow. A passing star does not scatter the cloud like a cue ball breaking a rack. What it mostly does is reshuffle. It changes the orientation of orbits, lowers some perihelia and raises others, and the result is a modest, drawn-out increase in the number of comets arriving at the inner solar system, spread across hundreds of thousands or millions of years, so gradual that if you were living through it you would notice nothing at all except that comets seemed, over the span of your entire civilization, very slightly more common than they used to be. Nobody alive will see it. Nothing that currently exists on Earth in any recognizable form will see it. 1.25 million years is roughly 5 times longer than our species has existed. But it will happen, it is calculable, it is in the catalogue, and it is closer every time we look. So the shell has a door, other stars come through it, one came through during our own history, and another is on its way. Which raises a question that has been sitting underneath this entire video, and which I have been carefully not asking. If our solar system has a shell like this, and if that shell reaches a quarter to halfway to the next star, then what does the next star have? In October of 2017, a survey telescope in Hawaii found an object moving through the solar system that was not going to stay. You can tell immediately from the orbit. Every object bound to the Sun has a closed path, an ellipse, however stretched. This one did not. Its trajectory was open. It had come in from outside, swung round the Sun, and was already leaving, and it was never going to come back. Remember the graph from earlier, the one with the Oort spike crowded up against zero? An object like this does not appear in the spike. It appears on the other side of zero entirely, in negative territory, which is the cleanest possible signature of something that does not belong to us. The team in Hawaii named it Oumuamua, from the Hawaiian, meaning roughly a messenger from afar arriving first. It was the first confirmed interstellar object anyone had ever seen. It was elongated, tumbling, oddly reflective, and it displayed a small acceleration that gravity alone could not account for and that has never been entirely explained. It is gone now, permanently, and we will never learn anything more about it. 2 years later, in August of 2019, the second arrived. To I, Borisov, and this one was unambiguous. It had a coma and a tail and behaved in every visible respect like an ordinary comet, except that it was not from here. When astronomers measured its composition, they found it unusually rich in carbon monoxide compared with comets from our own system, which suggests it formed in a colder region around whatever star it came from. That is a remarkable thing to be able to say. We measured the temperature of the outer part of another planetary system by catching a piece of it as it went past. And on the 1st of July 2025, the third one turned up. It was picked up by the Asteroid Terrestrial Impact Last Alert System, the ATLAS survey, from its station at Rio Hurtado in Chile, and it was catalogued as 3I Atlas. Hubble looked at it in early August and captured a plume of dust coming off its sun-warmed side and the beginnings of a tail. It reached its closest approach to the Sun at the end of October that year and has been on its way out ever since. Current thinking is that it had been drifting through interstellar space for many billions of years before it happened to encounter us. 3 objects in 8 years. And here is the thing about that number. Before the first one, nobody expected them to be this common. The pre-discovery estimates suggested such objects should be rare enough that finding one would be a matter of luck. Finding 3 in under a decade forced a substantial upward revision of how densely the space between the stars must be populated with this material. There is one thing we have tried and failed to do with all 3 of them, and the failure is instructive. In each case, astronomers ran the trajectory backwards to try to identify where the object came from, which star ejected it, and in each case the answer was no idea. The reason is that an object drifting through the galaxy does not travel in a straight line. It orbits the galactic center just as the Sun does, and it is perturbed by everything it passes. After a few million years, any memory of its origin has been comprehensively erased from its path. So we have 3 physical objects from 3 other planetary systems, we have measured 2 of them in some chemical detail, and we cannot say which stars they belong to and never will. That situation is about to change in one respect at least. The Vera C. Rubin Observatory, which we mentioned earlier for its effect on comet statistics, is expected to raise the discovery rate of interstellar objects substantially, potentially to several per year rather than 1 every few years, which means that within a decade or so the sample may grow from 3 to dozens, and questions that are currently unanswerable in principle become merely difficult. So let me put the chain together, because it leads somewhere I did not expect the first time I followed it. We know the Oort Cloud was built by throwing. The giant planets scattered icy bodies outward, the galaxy caught some of them, and the ones that were caught became the shell. But that same process, the same violent early sorting, also threw an enormous quantity of material out of the solar system entirely, not into a distant orbit, out, gone. Modelling suggests the mass we ejected into the galaxy is comparable to, or greater than, the mass we managed to keep. Now apply that to every other star. Every star that formed planets went through the same process. Every one of them threw material outward, kept some of it in a shell, and lost the rest to the galaxy. Interstellar objects, then, are not exotic. They are the overflow. They are what every planetary system spills while it is being assembled, and there are as many of them out there as there are stars that have ever built planets, multiplied by however much each of them threw away, which means the space between the stars is not empty of solar system debris. It is full of it. And now hold that against the number NASA gives for the size of our own shell. The Oort Cloud extends perhaps 1/4 to halfway from our Sun to the next star. If ours reaches halfway, and theirs reaches back, then there is no gap. That is the moment this stops being a video about our solar system. We have spent the last hour and a half building the idea of an edge, a boundary, a place where our system ends and the rest of the universe begins, and the arithmetic has just quietly removed it. If every star is surrounded by a shell of dark ice reaching a substantial fraction of the way to its neighbours, then the picture of the galaxy you are carrying, bright points separated by emptiness, is wrong in the same way the classroom diagram was wrong. It is not stars in a void. It is a continuous, cold, almost entirely invisible fog of icy bodies, filling the space between everything, with stars lit inside it like lamps in weather. Nobody has ever seen ours. Nobody has ever seen anybody else's either. No Oort Cloud has ever been detected around another star, and there is no realistic prospect of detecting one soon. The entire structure I have just described, the one that fills the galaxy, is inferred from the same kind of reasoning Jan Oort used on 19 comets, extended outward by one further step, and it has a consequence that runs in the other direction too, which is my favourite detail in this whole subject. NASA notes, in the same paragraph where they describe how the Oort Cloud formed, that it could also capture objects that did not form in the solar system. Read that carefully. If every star throws material out, and if every star is surrounded by an enormous weakly bound region where slow-moving debris can be gathered up, then the traffic is two-way. Some fraction of the objects in our own Oort Cloud may never have been ours at all. They may have formed around another star, been thrown out of it, drifted for millions or billions of years, and been quietly collected by the Sun on its way around the galaxy. Which means that when the next long-period comet arrives, when somebody, somewhere, walks outside on a clear night in the coming years and sees a faint smudge that was not there last month, there is no guarantee it started here. It may be a piece of the solar system, returning after 4.5 billion years in the dark, or it may be a piece of somewhere else, picked up in passing, that has been part of our system for so long that the distinction has stopped meaning anything. There is even a version of this that runs backwards into the Sun's own childhood, We talked a moment ago about the cluster the Sun was born in. Hundreds or thousands of stars packed close together, passing each other at distances that would be unthinkable now. During that period, every one of those stars was throwing planetesimals outward, and every one of them was surrounded by a region capable of catching slow-moving debris. Simulations of that environment suggest the young stars did not simply lose material to the galaxy, they swapped it. Substantial quantities of planetesimals may have been traded between siblings before the cluster dispersed and the stars went their separate ways. If that is right, then some of the objects in our Oort cloud tonight are not merely from somewhere else. They are from a specific set of somewhere else's. The Sun's brothers and sisters, scattered now across the galaxy, unidentifiable, carrying pieces of us in exchange. We have spent this whole video trying to find the edge of the solar system. It is beginning to look as though the reason we cannot find it is not that it is far away. It is that there isn't one. I promised you the number, so let me give it to you properly, and then let me tell you why it does not do what you expect it to do. The Oort cloud begins somewhere between 2,000 and 5,000 times the distance from the Earth to the Sun. It ends somewhere between 10,000 and 100,000. NASA's headline figure for the region as a whole is 5,000 to 100,000 astronomical units. Jan Oort's own estimate from the 19 comets was 50 to 150,000. In miles, the outer edge is roughly 9,300,000,000,000. In light years, it is about 1.5. In light time, it is 18 months. There. That is the answer, and I suspect you can feel that it has done almost nothing to you. That is not your failure. It is the failure of the number, and it is why I have been holding it back all night. Because the interesting thing about the distance to the Oort cloud is not its size. It is what happens to your instruments on the way out. So let us finish the list. Miles broke first, and they broke instantly, because miles are a walking unit and this is not a walk. The astronomical unit broke next, and it broke around 1,000, the point at which a unit anchored to the Earth's orbit stops helping, because out there the Earth's orbit is not merely small, it is invisible. From the outer Oort cloud, the Earth would sit 200,000ths of a second of arc from the Sun and be 10 billion times fainter still. The ruler we built this whole subject on cannot be seen from the far end of the thing it measures. Light broke third, and it broke in the worst possible way, which is that it did not break at all. It gave us 17 hours to the heliopause, the entire reach of the human species, every mission, every landing, every photograph, every object we have ever built, fitting comfortably inside a single day of light time, and then it gave us 18 months to the outer edge, 13,000 hours against 17, a factor of 770. Everything we have ever done is 1/770th of the way out, measured in the only currency the universe has ever agreed to accept. Voyager broke fourth, 300 years to the near edge, 30,000 years to cross, and a spacecraft that will be cold and silent for 270 years before it arrives at a boundary it could not detect if it were still awake. Kepler's laws broke fifth. A single orbit out there takes 11 million years at 50,000 astronomical units, and something like 32 million at 100,000. One lap. 1 year, in the local sense of the word. There are objects out there for which the entire history of the primate order has not been long enough to complete a single circuit of the Sun, and human history broke last. 30,000 years of Voyager's crossing contains every civilization, every language, every piece of music, every war, every idea anyone has ever had, twice over, with room to spare. Every ruler snapped, not at the same point, and not for the same reason. And that sequence, that steady, patient, one-by-one failure of every measuring instrument we own, is what the distance to the Oort cloud actually is. It is not 9 trillion miles. It is the range over which human comprehension runs out of equipment. But there is a further step, and it is the one I have genuinely been saving. The reason we cannot pin this distance down to better than a factor of 10 is not that our instruments are inadequate. It is that the thing we are trying to measure is not a location. The outer edge of the Oort cloud sits at roughly the same distance as the Sun's Hill sphere, the surface at which the Sun's gravity finally loses its argument with the Milky Way. And that is not a coincidence. It is the definition. The Oort cloud does not stop because the objects run out. It stops because the ownership does. So there is no line out there. There is nothing to cross. There is a long, slow, dark gradient in which the Sun's claim on the things around it gets weaker and weaker, and the galaxies get stronger, and at no point along that gradient is there a moment where you could say, there, that was it. We are outside now. The solar system does not have an edge. It has a balance of power, negotiated continuously for 4.5 billion years, renegotiated every time the sun carries it around the galaxy, and reopened entirely whenever another star walks through, as one did 70,000 years ago, while people were alive, and as one will again in 1.25 million years, closer. That is why the distance melts, not because it is large, because when you go looking for the far end of it, there is nothing there to find. I would like you to be somewhere for one last moment tonight. You're 100,000 astronomical units out, as far as anything is ever said to be, technically still inside the solar system, though you now know what that phrase is worth. The sky around you is entirely stars. There is no Milky Way band any brighter than it is from your garden, because you have not gone anywhere on a galactic scale. You have moved about 1/500th of the way to the nearest star. The constellations are almost exactly as you know them. If you have ever learned the sky, you could still navigate by it. Find the sun. It is there. Magnitude plus 0.8. A clean white point of light, roughly the 12th brightest star in that sky. Comparable to Altair. You could pick it out if you knew where to look, and you could very easily lose it if you did not. It has no disk. At this distance it subtends about 200ths of a second of arc, which means no eye and no unaided instrument would ever resolve it as anything but a point. It gives you nothing. Sunlight out here is 10 billion times weaker than at the Earth, something in the region of a 10 millionth of a watt falling on each square meter, which is not warmth by any definition. You could stare at it directly, indefinitely, and feel nothing at all. And on the other side of the sky, Alpha Centauri hangs at a comparable brightness, and there is nothing in the appearance of either one that tells you which of them is home. Somewhere near you, perhaps 10 astronomical units away, the distance from the Sun to Saturn, there is a mountain of black ice you cannot see, and it has been in orbit around that faint white point for 4.5 billion years, and it has never once had a neighbour close enough to notice. NASA said they coast along their orbits like lazy moths around a porch light. I have thought about that image a great deal while making this, and I think it is exactly right, and I think it means something completely different from what it sounds like. Because out here, the porch light is a star you could lose in a crowded sky. The moths are separated from one another by the width of the planetary system. They have never seen the light they are circling as anything more than a point. They have never seen each other at all, and they have been doing it in silence at 3 degrees above absolute zero since before the Earth had a surface you could stand on. That is the porch light. That is the moth. That is where the solar system actually ends. Except that it does not end, which was the whole point. Nobody has ever seen it. 76 years after Jan Oort worked it out from 19 numbers on a page, that sentence is still true, and I have stopped being able to decide whether it is the most impressive thing in planetary science or the most humbling. We described the outer boundary of our own solar system before we had put anything into orbit. We have not managed to photograph it since. We can tell you its approximate radius, its likely population, its probable mass, its formation history, and the name of the star that will pass through it in 1.25 million years, and we cannot show you a single object in it. And I want to be clear that this is not a temporary situation waiting on better funding. The reasons it has never been seen are physical, and each one closes a different door. The objects are individually small, a few kilometers across at typical size. Their surfaces reflect about 4% of the light that reaches them, and the light reaching them is 10 billion times weaker than sunlight here, so there is essentially nothing to reflect. Their temperature is a few degrees above absolute zero, so what they radiate comes out in the far infrared at around 1 millimeter in wavelength, at intensities buried under everything else in the sky. Their total mass is at most a few Earths spread across 1.5 light years, so their combined gravity bends nothing measurably. And they are so thinly distributed that the chance of any one of them passing in front of a background star while a telescope happens to be watching is negligible. Reflection, emission, gravity, occultation. Those are the 4 ways we detect anything in the universe, and the Oort Cloud defeats all 4 for 4 separate reasons. It is not concealed. It is simply spread out beyond the point at which any of our methods have anything to work with. Here is the last thing, and then I will let you go. Everything you learned about the solar system, the 8 planets, the 2 belts, the neat diagram with the sun on the left, occupies the innermost 3/10,000ths of the radius of the thing it claims to depict, 0.03 of 1%. And because volume goes as the cube of the radius, the entire planetary system, every world and moon and mission and photograph, takes up about 27 parts per trillion of the space the sun holds. 27 parts per trillion. The rest is dark and cold and almost empty, and it is full of more individual worlds than everything else combined, and it goes on and on without ever quite stopping, until at some point that nobody can mark, it has simply become the galaxy instead. I started tonight by telling you that the picture of the solar system in your head was wrong in a very specific way, and I want to close by being precise about the correction, because it is not the one you would expect. The problem was never that the diagram was too small. Everybody knows the diagram is not to scale. That is the first thing anyone is told about it. The problem is that it has a border. It ends. There is a line drawn around the outside of the solar system, and inside the line is us, and outside the line is everything else, and that line does not exist and never did. There is no membrane. There is no threshold. There is no moment at which anything leaves. Voyager did not leave in 2012, and it will not leave in the 23rd century, and it will not leave in 30,000 years either. It will simply, at some unmarkable point, be closer to being somebody else's than it is to being ours. The thing that melts, in the end, is not the distance. It is the idea that there was an inside and an outside to begin with, and the strangest part, to me, is how gentle it is. There is no drama out there. Nothing collides. Nothing erupts. The most extreme place in the solar system is also the quietest, 1 trillion mountains of black ice, moving slower than aircraft in the dark, around a light too faint to warm them, on orbits that take longer than the age of our entire order of mammals to complete once. They have been doing that since before the Earth had oceans. They will still be doing it long after the sun has stopped being the kind of star that makes oceans possible, and every so often one of them gets a small push it did not ask for and starts to fall, and takes a few million years about it, and eventually somebody down here walks outside on a cold night and looks up and sees it.